Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. I'm Laure Zana, faculty at New York University, and together with my colleagues Philippe Stier from the University of Oxford, Duncan Watson-Paris from the University of San Diego, and Tom Buechler from the University of Lausanne, we welcome you to the AI for Good event on AI for climate science organized by ITU. So we are absolutely delighted to host our first speakers of this returning series. Professor Chris Bretherton from AI2 and the University of Washington will be presenting on AI for climate modeling from present to future. As a reminder, the audience can leave questions in the chat room that will be answered during the Q&A section. But let's get started. Chris, the floor is yours.
Thanks very much, Laura. Let me just get started by sharing my screen. I think I'm sharing right now.
It's perfect. We can see your screen.
Great. Thanks very much. So I'd like to kick off this series first by thanking the organizers for inviting me, and then also to talk in general about AI for climate modeling, present and future. And I'd like to start also by thanking the team of people who work with me, shown here on the first slide, as well as our collaborating external partners, M2 Lines, which Laura Zana is actually a part of, GFDL, Lawrence Livermore Labs, and NVIDIA. So it's important to recognize that AI is standing on the shoulders of giants when it comes to weather and climate modeling. Physically based weather and climate models have told us a great deal about our climate that we have right now, and also what we're likely to see in the next century. And it's important to reflect on the reasons why it works, and also how AI can really help make it work better. Some design principles of physically based weather and climate modeling is first, based on a grid that covers the different components of the Earth system, the atmosphere, the ocean, land, ice. And those components are typically designed in a modular way. This allows the model to sort of separate the complexity of the different components and their interactions in a physically plausible way. The individual components are designed or represented in using algorithms that are physically or empirically based and designed to generalize across climates. And in a typical Earth system model, climate is simulated as the statistics of all of the processes acting naturally on their internal timescale. So it's the statistics of weather interacting with ocean currents, with land, with ice. And in particular, this means that, in fact, the very same model can be used for prediction at short timescales and climate projection or paleoclimate at the very longest timescales, so seamless prediction. And in this sense, it's sort of analogous to foundation models in machine learning, which can be where you have one model that you can fine-tune for many applications, but in a very different way. Well, how can machine learning or AI help with this process? The goal here is we hope to make weather and climate models, especially climate models in this particular talk, more accurate, faster, and more affordable and generally accessible through use of easier programming languages for people to learn. There are a couple of different strategies. The simplest form of machine learning is just post-processing, taking an existing model, trying to correct its biases. Another approach is a hybrid approach where machine learning replaces or corrects part of the model, for instance, the atmospheric model, and most of what I'll talk about. The approach I'll spend the most time on here is called full model replacement, where we replace the entire global evolution of the system we're most interested in by machine learning. And one special case of this, which is important for the model I'm most focused on, is full model emulation, where we use this to actually emulate an existing physics-based global atmosphere model. Now, I, in fact, was a presenter in 2021, the last time AI for Good had a climate modeling webinar series, which makes it sort of appropriate that I'm kicking off this series today. Noah Brenowitz and I talked in 2021, and it's instructive to think about what we talked about. So at that time, we talked about something called corrective machine learning, which involved trying to learn a correction to an existing climate model to make it more accurate in some sense, either better following the evolution of observations or some other more accurate model. And Noah talked about machine learning of physical parameterizations. At that time, there'd also been some early work on full model replacement for weather forecasting. Then, more or less in the year after that webinar series, the AI weather forecasting tsunami rolled in, and there were many groups, starting with Ryan Keisler, then Forecast.net, Pangu, GraphCast, GenCast, and so on, that rapidly advanced the state of AI weather forecasting to the point where it went beyond the skill of conventional physics-based weather forecasts. One model I'll note here is Neural GCM, which had a different architecture from the other models. Instead of using full model replacement, it used hybrid modeling and showed that that can actually compete in this arena as well. And I think the real testament to the impact of this is that the world's leading weather forecast agency, the European Center, hired an AI team and operationalized their own AI-based forecast system because the skill of the AI models was in fact superior to their own models. Now, these models mostly use this full model replacement architecture shown at the bottom, where you take the entire state of the global atmosphere or any other climate model component, which is more than 1 million variables at a typical resolution that might be used for a model like this of 1 to 2 degrees, and many more than that if it's used at a 1/4 degree resolution, like some of these models are for weather forecasting. That's then passed through what's called an encoder that basically turns this global state into a representation that's more optimal for the AI to work with. And then the encoded state is passed through different modules that do horizontal exchange of information between grid columns and processing of information within grid columns. So these really represent the sort of wind-driven and the remaining physics-driven parts of the evolution of the atmosphere. Then after some number of such cycles of exchange, this is passed through a decoder to predict the state of the atmosphere 6 to 24 hours later. And that's rolled out for an indefinite period of time. Now, This process is great. It can take a time step that's not limited by the time step of physics-based models. That's many times longer. It's optimized for GPUs, so it's very fast. But if you then try and take it on to longer timescales than weather forecast timescales, many machine learning weather forecast applications, which work very well, break down in months if applied to a more climate setting. So for instance, what's shown in this figure is 500 millibar height, zonally averaged as a function of latitude over the course of a year from January through December, shown at the upper left for ERA5. And then rollouts of this forecast starting on January 1st using different leading weather forecast models. So Pangu and GraphCast, for instance. And what you see is, for instance, Pangu in the top middle, which is using, in this case, a 24-hour rollout timescale. It's continues to make a forecast, but the forecast doesn't ever follow the seasonal cycle. For GraphCast, it actually blows up after 3 months and gives a nonsensical forecast. But there are some architectures, such as John Venn and Dale Durant's deep learning weather prediction model, which are able to follow the seasonal cycle. Another one is the SFNO, spherical Fourier neural operator architecture that's used in the second generation of ForecastNet designed by NVIDIA. So we do have a couple of things that, architectures which seem to work okay, possibly for longer term climate applications. So what we then want to do is see, well, okay, based on this technology, which works so well from weather, is it possible to do something similar for climate AI? So there are some additional considerations. One of them is that we need to consider the ocean. Even for seasonal or ENSO, we have to include upper ocean evolution. But we can do so in a simple fashion. AI-based weather forecast models typically only predict a couple of things, if any, about the ocean. They might predict the 2-meter temperature, which is not an ocean variable, but sort of can be a proxy for the sea surface temperature over the ocean. Or they'll predict the surface temperature, but nothing more about the ocean or land surface. There are some AI-based seasonal forecast models, including a model called Orca from China, for instance, which do include a multi-layer AI-based ocean. However, if we want to run these kinds of models out for periods of decades or centuries, there are a lot of modeling challenges. One of them is, well, can we even, just thinking about the force response of the atmosphere to other forcers like the ocean, or to just changes in greenhouse gases, can we correctly represent that over periods of many years? Do we have multi-year climate stability and accuracy? More difficult, can we simulate coupled atmosphere-ocean variability and trends over periods of decades? And most difficult, can we generalize past the observed present to accurately or robustly predict past and future climates that are not currently seen? So these are big challenges. We don't have the answers to all of these, but the state of the art is changing fast. I'd like to talk about 3 examples of models that I think have actually been impactful in raising the bar, other than our own efforts at AI2. One of them is called Neural GCM. It was developed at Google Research. It's notable because it's a hybrid model. It has a conventionally designed dynamical core using the so-called spectral method, but it's coded in the machine learning language JAX that allows us to use the mechanics of machine learning, stochastic gradient descent, for optimizing what is learned in the model, which is the parameterized physics. So these are optimized by making forecasts with respect to what we see in the last 40 years of ERA5 reanalyses and making those forecasts as good as they can over periods of a few days. And neural GCM, unlike hybrid models that came before it, including ones that my own group developed, was because of this ML differentiable die-core able to produce not only accurate weather forecasts, but accurate representation of the climate change over the last 40 years. So for instance, the plots on the right show that over the course of a year, if you take a look at the global mean temperature at 850 hectopascals, model is accurately representing the annual cycle, and the plot on the bottom shows that it's also able to accurately represent the observed rise of temperature over the last global mean temperature over the last 40 years, when forced by the actual observed ocean temperatures. And not only that, it's able to reproduce its year-to-year variability associated mainly with El Niño. Another notable model is the deep learning Earth system model, a successor to Duran's DLWP model. This uses a different kind of architecture. It's a full model replacement using a UNet type model architecture. Again, it's trained on the ERA5, so it's limited to the current climate. It does include coupling to a very simple representation of the upper ocean. It's able to make a stable, accurate, repeating seasonal cycle with this coupled ocean representation. And it makes some form of El Niño, which has the right structure, but is quite a bit too weak. So it's starting to make progress toward this vision of a coupled atmosphere AI climate model. And the last model I want to call out is called C model. It was developed by Noah Brunowitz and colleagues at NVIDIA. And it has a whole different concept behind it. Basically, the idea is you take a reanalysis of, say, over the last 40 years, and you just create a sampler that can create what looks like a sample taken out of the distribution of possible weather states that could be created by that, that were sampled by that reanalysis. So it's not really trying to evolve the climate forward, it's just trying to sample it. But by conditionally sampling it, you can look for particular kinds of extreme weather events like tropical cyclones. And one thing it can do is sample what happens to the climate as the ocean temperature changes. And so it too is able to replicate the temperature increases in global mean surface air temperature over the last 40 years fairly well. Although if you take it outside its range of generalizability, say 1940 to 1980, where it didn't use any reanalysis data, then it doesn't know what to do anymore and just produces no trend. Okay, well, for the rest of this talk, then I'd like to focus on the approach that we've taken at AI2 called the AI2 Climate Emulator, or ACE. Not because it's the only game in town, but it's one I know about and one where I think I can show you kind of the progression of what's happened over the last 4 years and how we're becoming able to do increasingly ambitious tasks. So like DLESIM, this is a seamless full model replacement approach. Our strategic focus at AI2 has been on longer term climate, on accuracy of climate, of generalizability to unseen climates, although we do what some groups might consider cheating in that regard. So I'll talk about what our cheating approach is, and also on how we can couple different Earth system components on these longer climate timescales. So the cheat part of this is to generalize. What we have focused on is training on climate model output, as well as training on historical reanalysis. And the advantage of climate model output is you can run a climate model in any climate, and so you can train your model, your full model replacement on a diverse range of climates. That's great, but of course, now you're emulating a climate model. You're not expecting to get a better answer than that climate model. Instead, all you're doing is hoping to produce an AI application that can be a lot faster in coming to an answer, maybe hundreds to thousands of times faster than the original climate model, which has many advantages of its own. And our approach then was we start simple and then work toward more complicated situations. So we started by looking at a situation where we just use an annually repeating cycle of ocean temperature and fixed greenhouse gases. And then we've added more realism, historical SST changes, CO2 increases, considered ocean coupling, and so on. ACE, we typically run on a 100-kilometer grid horizontally. We predict 8 layers within the atmosphere. They're terrain-following layers, so that these allow us to add the mass within those layers to do column budgets, which is important. And another unique feature of ACE is that we include the prediction of boundary fluxes as part of our machine learning that we roll forward. These are diagnostic variables. They don't have memory from time step to time step, but we can accurately predict them at each rollout step. And so these allow us to construct budgets of moisture, energy, and mass rigorously. And in particular, that also allows us to constrain and enforce that those budgets are physically plausible. So the training setup then that we use is we have a certain set of prognostic input variables. These are the humidity, winds, temperature at our 8 layers at each grid point in the globe, plus the surface pressure. We then pass these through this method called spherical Fourier neural operator, which was developed in NVIDIA originally, and which appears to have some stability on climate timescales. And then we predict these things 6 hours later, and we also predict the surface fluxes. And at each time step, then we're also forcing with insolation and with sea surface temperatures. And the model is also given information about where there's land, where there's ocean, what the orography is, and so on. Here's an example of one of those radiation diagnostic fields, outgoing long-wave radiation at the top of the atmosphere, from 30 days of rollout between ACE and the model that it was emulating, which was a version of our national weather forecast model at the time. And so these were identically initialized, and after a while they ceased to become identical. But the main point here is that the statistical character of the ACE prediction here, where we have black regions of low OLR, say in the tropics, associated with deep convection and with mid-latitude storms, that those are very similar to those in the target model. And this stays that way over the entire 30-day period. So the point about this is we're able to, for an essentially indefinite period, emulate the statistical character of the reference model that we're trying to emulate. The prediction is slightly overly smooth. This is, again, a common feature of full model emulation. An important feature of ACE is that we can maintain budgets. And this is an example from our first paper on this. we take a look at the amount of water vapor in each atmospheric column, the total water path here, TWP. It's increased by evaporation into the column from the surface. Precipitation is a sink, and there can be a horizontal advective sink from mixing with other grid columns. And we can machine learn each of those terms separately, and we do as part of ACE. Add them together with the tendency and look if it matches the tendency that's coming from the evolution of the humidity in ACE. And if you look at the reference model, he's actually, the difference between these two is 0, no budget residual. That's shown in the upper right for a particular 6-hour time step. And then below is for ACE. Now, again, it's a 6-hour time step from into the rollout, so it's not, the weather isn't exactly the same. But again, the fields add to almost 0. So in this case, humidity was not exactly being conserved, but the machine learning is already doing a very good job of almost conserving it. This means that when you do try and exactly conserve humidity, you're not going to be messing up the machine learning you're already doing. It's just kind of a minor correction to this. So we've tried emulating a number of models using even this initial version of ACE. Another we emulated and the SFNO model, FE3GFS. We've also emulated the atmospheric component of the DOE climate model, E3SM version 2. And what's interesting there is we can take a look at precipitation bias of a 10-year climatology with a repeating SST. And ACE is such an accurate emulator of EAM-v2 that its precipitation biases averaged over those 10 years are much smaller than the biases of the model versus observation. So you would be able to look at ACE and think that it looked a lot like EAM-v2 as opposed to some other climate model. And you could definitely tell it was not emulating the observations. In addition, a nice feature is that not only can you get the extreme mean climate right, but you can get extremes such as precipitation extremes right as well. This is basically a PDF over 10 years of daily precipitation composite or across all grid points of the model. And so you can see that even out to the very extreme tails, ACE is basically replicating the reference model it's trying to emulate. Okay, well, now moving on to a more ambitious problem, though, then let's look at trying to emulate historical climate. We, in fact, emulated the period 1940 to 2020, and we both trained our model on reanalysis, that's ACE2 ERA5, and then we also trained it on a model forced by the same sea surface temperatures, which are, of course, increasing with time as were used in ERA5. And what's shown here then is a comparison of a variable total water path here, which tends to increase as the climate warms. And these are for 3 rollouts of ACE2 ERA5 using different initial conditions, and then for ERA5 itself. And again, you can see that ACE2 is able to replicate the trends and the interannual variability pretty well, given the expectations from natural interannual variability. In particular, the wiggles due to ENSO are being relatively well captured. So one thing to notice, what's different about ACE2? Well, one thing that's different is that it was enforcing conservation properties, dry air mass and moisture conservation. There were a variety of other architectural improvements. Another thing is that CO2 was actually used as one of the input features. So this model has some other interesting, nice characteristics. So for instance, one of them is it's very good at emulating tropical variability. So compared to ERA5, if we take a look at this plot, which shows a Hoffman diagram of precipitation versus time over a 2-year period. This is precipitation, I think, averaged between 10 south to 10 north as a function of longitude. The stripes here are variability associated mainly with the Madden-Julian oscillation. And what you should look at is kind of the texture of these series. And you can see the texture, the amplitude of the variability, its speed of propagation from west to east is very similar to ERA5, much better than a typical climate model would produce. Similarly, the tracks of tropical cyclones are very well replicated in AIS2's emulation as well. And lastly, this model accurately responds to El Niño variability. So now this is forced El Niño variability. We're specifying the SST, but we can still ask, well, does the precipitation, for instance, or other fields respond correctly to the forcing? And so comparing ERA5 in the lower left with AIS2, trained on ERA5, you can see that the pattern of the regression of precipitation on Niño 3.4, which is kind of a measure of El Niño that's very commonly used, they're almost indistinguishable. Similarly, if we train AIS2 on SHIELD, a different model from NOAA, which is similar to the FE3 GFS model, again, the pattern of variability in AIS2 SHIELD is very similar to that in SHIELD. Comparing that to a model which was only trained on climatological SSTs rather than the historically observed SSTs, you can see the pattern is there, but the amplitude is much weaker. So it is necessary to train on the full spectrum of historical variability to capture historical variability in the emulator. Now, I just want to mention then in passing that we have proposed and specified an intercomparison called AIMIP phase 1, where models are forced by SSTs from 1979 to 2024, more or less following the specification of the CMIP atmospheric model intercomparison project, AMIP project. One of the goals here is to make sure that emulators can produce outputs in a form that's suitable for the CMIP community to evaluate, so that these emulators can be socialized into the conventional climate modeling community and tested against other models, and that the community can gain confidence that the models are reasonable, not just because we say that they are, but because they can evaluate all their outputs and find that they are for themselves. So here's information about how to participate. So now what I'd like to do is talk about a different application of AI within the same framework. So that's to do downscaling. So these models are run at relatively coarse resolution, say 1 degree resolution, in part for speed and in part because they're pretty accurate at that resolution. But we can now run global storm resolving models at, say, 3-kilometer resolution, which produce almost photorealistic outputs and maybe are more accurate, especially for climate change. But also, we can imagine emulating them. And in fact, that's something we have done at AI2 in collaboration with GFDL, using their so-called X-SHIELD model, which is, again, a version of the national forecast model that's but run on a 3-kilometer grid. And this picture then shows an example snapshot from that model of surface precipitation rate taken from a 10-year simulation that was recently completed by Lucas Harris's group at GFDL. So what we do here is first we use it to try and form an emulator of this model. And it turns out 10 years is just about the bare minimum we can use for that, but we're able to make an emulator of this model. So to do that, what we do is we coarsen the outputs for this model in line while the model is running to a 100-kilometer resolution suitable for the emulator. And we then train a version of AIS2 that is designed to match that. And this picture maybe makes it look like it's not matching it too well, but the measles here are all due to the fact that the version that we use here is stochastic, because it actually will work better for our downscaling purposes. And the blue dots here are regions of very light precipitation from the stochastic model of ACE that weren't present in the original shield, but they're actually very minor perturbations to zero precipitation. Then we also use this 100-kilometer coarsened information as part of formulating a downscaling model. So the idea here is, suppose we could run this version of ACE at 100 kilometers, but then downscale the results to 3 kilometers by using the results of this 3-kilometer X-shield simulation. So the idea then is that what you want to do in downscaling, you use an approach called diffusion modeling, in particular corrective diffusion or core diff, where basically you train the model to go from a coarse resolution of data, surface precipitation data, to the much finer realizations which you would get at 3 kilometers. So by pairing lots of versions of this, using 9 of those 10 years of data globally, we're able to then create actually a very remarkably accurate downscaling approach. So what it does then is it takes images like this stochastic ACE forecast on the left, combine it with the diffusion modeling downscaling, and then you're able to downscale all the individual events from 100 kilometers down to 3 kilometers. And corrective diffusion is a generative approach. It's stochastic, so it produces different realizations at 3 kilometers, which would be consistent with the coarse resolution simulation shown on the bottom, the left one of the 3 panels on the bottom right. So downscaling is another very exciting application. And what's remarkable is we're downscaling from 100 to 3 kilometers, which means that at 100 kilometers, things like a tropical cyclone are barely even detectable. So at the left, this is the input data for the downscaling. You would have a tough time saying there was a tropical cyclone there. But the machine learning knows it's there, and it makes the prediction in the middle, which is actually a lot like what X-shield was predicting at the same time at the right. Similarly, it's able to do climate pretty well. So if you look at the time mean precipitation over the Northwest USA here, in the coarse model, ACE, this is time mean over, I think, 10 years. No, actually, I'm not sure it's 10 years. No, it's 9 years, I think. Then the downscaling then produces the time mean precipitation. Now it's producing this out of a bunch of 6-hour snapshots. So it's not producing the time mean directly. And then you compare that to the time mean of the original reference, X-shield 3-kilometer data. You again see a remarkable agreement. So you're able to replicate then all the details of the time mean precipitation, including orographic precipitation, rain shadows, etc. So another application of a model like this is that we can already do seasonal forecasting with it. And so the UK Met Office, for instance, took the ACE2 model trained on ERA5. And of course, ACE2 itself doesn't predict sea surface temperature. So they just persisted existing sea surface temperature anomalies from each 1st of November, and then used them to make forecasts for the December to February season using ACE with those persisted SST anomalies. And remarkably, what they found is that they were able to predict the seasonal climate almost as well as the Met Office's operational seasonal forecast application, GLOSY, at, of course, much reduced computational cost, and despite the fact that there is no prediction of SST anomalies going on here. So this is also very promising for the future of these models for seasonal forecasting. And other models have also demonstrated a lot of seasonal forecasting skill. Now let's talk about coupling models like ACE2. So our first shot at this was we wanted to do a form of coupling which would allow us to explore the climate generalizability of models like ACE. So we started by coupling to a slab-ocean model. So a slab-ocean model is a purely thermodynamic model. It doesn't have any ocean dynamics in it. You basically have the advantage, though, that this model can be coded in Fortran, and so run with the existing reference atmosphere model. And it can also equally easily be coded in machine learning language and then coupled to ACE. So we can run a model like this with different greenhouse gas concentrations, run a reference model with those greenhouse gas concentrations, use that for training ACE2, and now we have a model that we can use across climates, ideally. But there's some question about this. First, again, we're testing, the training that we're doing is using 6-hour forecasts. Can we expect to get the different climate from these different cases when, over the course of 6 hours, the effect of quadrupling CO2 is pretty negligible? It's like a needle in a haystack. And can we generalize to other climate change scenarios? Those are really big questions. So we have investigated these, and we find we're actually pretty encouraging results. So one thing we can do, for instance, is we can train them. We can test, well, how well does the model do on those 3 climates on which it was tested, and it does a very good job. But also it does a good job with intermediate climates. So we also tested it on a 3 times CO2 climate, and we differenced the 3 times CO2 temperature, surface temperature, with the surface temperature of the 1 times CO2 climate. And we saw to what extent can we replicate the warming seen in the physics-based climate model at the left with ACE2. And you can see from this picture that ACE is replicating the time mean warming very accurately, both in amplitude and in spatial pattern, even though 3 times CO2 is an out of sample CO2 concentration. So this is showing you are doing a reasonable job with climate change. There are other things which are much harder, though. And so one of them actually is a classic test of climate models called abrupt 4 times CO2, where you start with a coupled climate model, and then you quadruple CO2, and you watch the model come to equilibrium. So if you take a look at the original physics-based model, what happens when you do this is the black solid line shown at left. And what's shown here is only the first 90 days of what could be a 200-year integration for this thing to come into equilibrium. But immediately what we found is with our ACE2 model coupled to a slab-ocean model, it warmed the atmosphere way, way too fast. That's the light blue line. So one thing we've been working on is physics-based solutions to make this more realistic, that involve, for instance, separating out the radiative effects of heating from other aspects of the model, forcing the model to conserve energy, changing the model architecture a bit, and then we're able to come closer, the brown line, to what is actually observed with the physics-based model, the black line, in the terms of the initial response. So it's encouraging, but this is a much more challenging problem. It shows that generalization to other climate scenarios should not be taken for granted at all. It's quite a challenge, even if you can train on quite a few climates. So lastly, what I want to do is talk about a coupled emulator. So this is coupling ACE. Our atmospheric emulator with the Samudra, which is a project of the M2 Lines philanthropically supported project. And Laura is, in fact, was one of the leaders in developing Samudra. So Samudra is also a full depth emulator now of the ocean, spanning 19 layers with 1 degree resolution. It uses a longer time step, a rollout step of 5 days, and it's coupled via the surface fluxes to the atmosphere emulator. We added interactive learned sea ice so that we could use this for climate time scales. And then we used a pre-industrial run of GFDL's CM4, coupled climate model, for training and for testing. So this is around well, we have an equilibrium climate, but it also has natural variability. And so we train on 160 years, we test on 40 remaining years of our simulation. And we find that the coupled emulator is able to stay stable. It produces surface temperatures over both land and ocean that are relatively unbiased with an RMSE of only a third of a degree K, which would be enviable in a conventional climate model, trying to, say, replicate the current climate. And now, of course, this is the bias with respect to CM4. And more notably, though, we're also able to replicate the natural variability, basically the ENSO of this model pretty accurately. So black here is the Niño 3.4 SST anomaly from CM4, from 40-year holdout period. And orange is from our emulator, Samudrace, as we call it, and showing that the amplitude of variability is getting on for as large as the amplitude of the variability in CM4. And the pattern of variability is actually very realistic too compared to CM4. In addition, the seasonal cycle of sea ice is actually also emulated very well on average. That's shown for the northern and southern hemisphere here left. And the bias in the sea ice fraction, time mean bias, is quite small as well. So in summary then, this is an active area of research. Several groups are progressing toward accurate AI model of the present climate, skillful for intraseasonal and seasonal forecasting. That's great. That's a very important application. What we've been trying to do at AI2 is more focused on the longer time scales. And what we've shown is that that's also, I think, a feasible problem, at least if you're trying to emulate an existing climate model. We don't have a similarly good approach for going way out of sample using purely historical data to emulate future climates accurately. That's an important future problem, one of which people like Tom Beukler are very interested in, for instance. But our emulator is very skillful in AMIP configurations, in slab-ocean perturbed CO2 configurations when suitably trained. And it's able to capture the forced response, not just to greenhouse gases, but also to SST variability. It's able to be coupled to an emulator of the ocean with similar characteristics. And it's about 100 to 1,000 times faster to run than the reference model. So it's very suitable for ensemble simulations. And furthermore, we've built in integrated AI-based downscaling that is also very fast and flexible. So we're still headed toward our ultimate goal of a model that you could use for, say, CMIP-7, a coupled emulator for general climate change scenarios with diverse radiative forcings. But we and the rest of the field have made a lot of progress toward that in the last 4 years. And I think the next 4 years will be, again, very exciting. So thanks.
Right. Thank you very much, Chris. Absolutely fascinating and very exciting to see the progress. And as you mentioned, you were one of the speakers, in the original series. So it's pretty amazing to see everything that has happened in the past few years. Okay, so we have quite a few questions actually for you. So I'm gonna kick things off. And so one of them is pretty interesting. So the first one is, can emulators trained only on pre-tipping point climate data can accurately predict system behavior near or beyond the tipping point?
Yeah, well,
So
that's a
you're
great
alluding
question.
at that one, right? But yeah, this is a great
Right.
question.
I mean, that's a classic out of sample test. And I would say an emulator would not be my first choice of things to rely on right now. Once we have once or if we ever succeed in developing AI emulators that demonstrably seem to be able to go from information you only knew in the present climate to information which was characteristic of future climates. And a way of testing this might be in a perfect model world where you have an emulator of a climate model, and then you only give it historical information from simulations of the climate model, but then it has to predict the future climate of that climate model. Once or if we can do that with AI, then we might be in a position to think about the tipping point problem. But that's tough for even regular climate models. And anyhow, I would be crossing my fingers, and uh, I'll leave that problem for the next generation.
Yeah, fair enough. All right. Okay. So we have another question which is multi-part. So I'm gonna try to summarize it a little bit. So you mentioned two things. One is that you've SFNOs have basically shown some good potential for stability on kind of longer timescales. And so the question is twofold, right? So one, why using SFNOs compare to, for example, diffusion model? And why would the SFNO actually be more stable? So I'm kind of summarizing pieces of it.
All right. Well, first I should say it's serendipity that we're using SFNO. It wasn't actually a choice that was made based in the knowledge that SFNO was stable. When we actually started doing this, we were using the initial version of NVIDIA's forecast net. We weren't using it because of any good stability properties it had. In fact, we knew it went unstable after 10 days. We were using it instead because it was open source code and because I knew the developers. I felt like, okay, as this model improves, we might be able to take advantage of it. So it was kind of more of a leveraging thing. And actually, quite frankly, I think that's a very important thing in general, is we have to lean on each other to make good AI because every group is good at different things and we are better if we work together. But then partly as a result of conversations with NVIDIA and partly because they were doing it, Boris Bonev was doing this already, they were moving to a better version of ForecastNet using the SFNO architecture. And it just so happened that that architecture is very stable for climate for reasons that I can hypothesize about, but even right now, I
Mhm,
can't tell you for
mhm.
sure. While other architectures, even diffusion-based architectures based on rollout, are not necessarily as stable. They're harder to make stable. Um, and anyhow, so it's still a good subject for research, actually, about what makes a stable architecture. I think it's fair to say we don't know.
Yeah. All right. Philip, do you want to chime in?
Yeah, first of all, great talk, Chris. Really nice to see all the progress. Really impressive. I mean, I have to give you a little bit of a hard time, but the audience may not know Chris is not only living in the AI for climate space, but also an eminent expert on cloud feedbacks. So, given that we know that cloud feedbacks and potentially, say, errors to cloud interactions are the biggest uncertainty in current sort of climate projections, at least from the atmospheric component. Where do you see the strategy really to tackle these? Because we don't trust current climate models to do those well yet. And you've spent a lot of time with high resolution, ultra high resolution LES to tackle some of this. But how do we tackle these big uncertainties that we at the moment don't do well in current climate models? Do you see a good strategy with your approach to get there?
Um, Yeah, well, I've always seen AI-based climate models as complementary rather than a replacement for physics-based climate models. So from that point of view, would still lean more heavily on global storm resolving models, perhaps things like ultraparameterization to provide sort of more physically based answers to that question. That said, I do think that there are we can at least think about problems involving cloud feedbacks in these models. So one of the things we've done with ACE is ACE doesn't actually predict clouds at all. So you might say, okay, well, what use would a model like that be for even thinking about cloud feedbacks? But one problem that people have been interested, or one analysis tool that people have used a lot in cloud feedbacks, in particular, in looking at the so-called pattern effect on cloud feedback, where the actual pattern of sea surface temperature affects the cloud distribution and affects the global radiation budget, and can therefore affect the rate at which the planet warms, so people have used something called sea surface temperature Green's functions, SST Green's functions. And so what they amount to doing is making a lot of simulations with a conventional climate model where you change the sea surface temperature in a patch and you look at what the radiative response is due to the change in clouds that accompany that. And we've looked at whether we can emulate that with an emulator for an existing model. And the answer is we can do a surprisingly good job. It's not perfect, but we've emulated the E3SM V3 atmospheric model, and it's able to do okay. So it's able to replicate all the things that cause clouds. It's able to sort of replicate the clouds of that model, but of course, there's no guarantee that those clouds are right, and the emulator isn't going to help you with that. But what it could do is allow you to leverage things like global storm resolving models, where it would be very expensive to do similar SST Green's function tests, and potentially allow you to do the what if of, well, if I could run that model for thousands of years, what would it say about pattern effects, for instance? So the ways I can imagine being able to use this information. But no, I don't see it as a replacement for physics yet.
Brilliant. Thanks. Yeah, we could talk
Yeah.
about it probably forever. But there's a question actually by Pierre Novak as well. Pierre asked a bit about, do you have some hope intention to skip the downscaling step at some point and instead to stably emulate just directly the high resolution?
Yeah, well, ask NVIDIA, because they're trying to do that right now. The main problem is that, one of the real attractions of AI-based emulators is they're very easy to use and they're very fast, and they're therefore very easy for the community to take over themselves or train another model. And by the time you're going to try and emulate a 3-kilometer model at 3 kilometers, that's actually a lot of computation. It's not as much computation as the original model, but it's not something that small groups are going to be able to do, or that you're going to be able to run in an academic setting. And so, and the other thing that's very strange or very different between AI models and regular physics-based models is resolution dependence. You can, for instance, emulate a 1-degree model at 4-degree resolution, and your emulator is almost as accurate in terms of the climate of that 1-degree model as a 1-degree emulator of that 1-degree model. So you don't need a high-resolution emulator to make a very accurate climate. And the reason is because all of the subgrid interactions, they're all folded into the training. They don't have to be folded into the physics that's actually represented explicitly in the model. And so there's a lot of attraction as a result for making a coarse emulator and then downscaling it rather than using the fine grid emulator in the first place.
Okay, so let's take one final question from Tim Palmer. So what Tim is, mentioning is, of course, one of the important, problems in climate and climate change is regarding the cooling trends in the, Niño 3 region, and whether or not it's anthropogenically false or not. And if we look at, the current generation of CMIP models, well, none of them can actually predict that. So the question would be, is it better to actually run a high resolution model or actually focus on really developing high resolution models? Or would AI-based, approaches could help us solve that problem?
Yeah, both. I mean, again, I can't emphasize that, and I think Tim would know this himself. There's no replacement for, resolving the physics as well as you can to get at these kinds of issues. But the problem then is you're stuck with all the computational constraints and remaining uncertainties you have there. And that's what AI can potentially help you explore. For instance, one of my personal visions for AI is that we could actually have say a 1-degree emulator for paleoclimate, which would allow us to actually simulate ice age cycles, but 10,000 years a day or something like that. So, to the point where and that's the kind of way that I feel like AI is transformative. It's not like it can substitute for new physics, but it can definitely leverage the models you have in ways that you otherwise couldn't do.
Perfect closing statement. I'll pass it on to Phillips. Thanks, Chris.
Brilliant, Chris. Thanks a lot. Well, I think this was a really nice kickoff to the series again. So thanks a lot, Chris, for getting us started. I should say I just checked. We haven't put all the upcoming talks already on the webpage, but they're coming soon. So people can, I think, sign up to the email list and you get updates. There's more to come, but this was a great start, and we could talk on forever, but unfortunately we have to stop. Thanks a lot again, Chris, and thanks a lot for joining.
Okay, well, thank you too. And thanks for everyone for listening.
Thanks again, everybody. Thanks, Chris.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.